let's continue our discussion for the finals. Okay, so this is the last topic or the last lesson that we will be discussing in finals, and it is entitled as titration. So it is very, very different to the past topics that I've been already discussed with you guys, because the past topics that I've already discussed with you guys is focused on calculation, while titration is basically focused on the application, meaning to say it is more on the experimentation. There is a procedure and there is a step-by-step process. So now, let's define first what is titration. Titration is a technique to determine the concentration of a known solution. Titration is the slow addition of one solution of known concentration, which is also called as a titrant or titrator, to a known volume of another solution of unknown concentration called titrant or analyte, until the reaction reaches neutralization, which is often indicated by a color change. So basically, when we say titration, it is a process in which we have to identify or we have to find the unknown solution. If we've already reached on finding the unknown solution, the name of the unknown solution, meaning to say we've already reached the end point or the end of the experimentation, called titration. Titration is also known as titrometry or volumetric titration. So let's proceed. So in as I've said a while ago, titration is not basically focused on the on the calculation, but hence it is focused on the steps, on the procedure, on how making or how to demonstrate the experimentation, which is called as the titration. So meaning to say, if we are focusing on the demonstration or in the experimentation, there is an elements involved. So elements of titration. So there are two elements of titration. We have the standard solution, or also known as the titrant or titrator. This is the solution that being added to the analyte, which is this solution is the unknown solution. Okay, did you get the point? So here, as you can see, we have in the illustration, this is how to picture out the experiment itself, okay, by titration. So we have to use a different laboratory apparatuses. We have to use ring stand, calibrated burette, and the beaker. So there is two reagent that is involved in titration. We have the NaOH and the HCl. So NaOH, basically, it is the standard solution or the titrant. That solution is being added to HCl, which is also called as the analyte. This is our unknown solution. Okay? So that is the element of titration. So now let's go on the equivalence point and the end point. So there is a big differences between the two processes. Why? Because in the equivalence point, this is the point when the reactants are done reacting. Okay, so meaning to say the equivalence point is an ideal point for the completion of titration. At the equivalence point, the correct amount of the standard solution must be added to fully react with the unknown concentration. So here, by explaining the description of the equivalent point, it being discussed that equivalence point is when the titrant and the analyte is equal in terms with their moles. Okay, in terms with their moles, if mole standard, in terms with their mole standard, if the titrant and the analyte is already equal, meaning to say you've already reached the equivalence point. While in the end point, it indicates once the equivalence point has been reached. So it is the indicated by some form of indicators which varies depending on what type of titration is being done. For example, if a color indicator is used, the solution will change color when the titration is at its end point. So the end point is basically we can identify the end point if there is a process called changes in color. Okay, change in color. So if you've reached already the end point, there is so-called process, there is so-called result in change in color, meaning to say that is your end point. So from the description itself, there is a differences between the two processes. Okay, to elaborate more about the endpoint, let's proceed on the illustration or picture. So here we can identify the good endpoint and the bad endpoint. For the good endpoint, as you can observe, there is a light color. Nag-change siya ng color. While in the bad endpoint, the more pa siya naging concentrated. The more darker yung color. So this is the bad endpoint, this is the good endpoint. Okay? I hope you've already understand what I'm saying. What is my point? Okay? So now, let's give the differences of equivalence point and endpoint. I've already mentioned it a while ago, but ulitin lang natin. So an endpoint is indicated by some form of indicator at the end of the titration. And if the process already changed in color, meaning to say you've already reached the endpoint. While the equivalence point is when the moles of the standard solution titrant is equal to the moles of a solution of unknown concentration, which is analyte. Okay, so as I've said a while ago, when we say we can reach the equivalence point if the both titrant and analyte is equal already in their moles. Okay, if there is so-called equal, now, meaning to say you've reached already the equivalence point. So now let's proceed. So now let's proceed to one of the apparatuses that being used in the experimentation, and that is called as the calibrated burette. It is the main piece of equipment required for titration method. Calibration is important because it is essential for the burette to be as accurate as possible in order to dispense very precise amount of liquid into the sample. So a burette is a long cylindrical piece of glass with an open top for pouring in the titrant. At the bottom, there is a carefully formed tip for dispensing. So basically, this is a certain description on how calibrated burette or how burette is being used in a titrant experimentation. Burettes is usually have a plastic stopper that can easily be turned to deliver mere fractions of drop of titrant if needed. Burettes come in many sizes and are marked in milliliters and fractions or of milliliters. Okay. So basically, burettes, as we all know, all of the burettes has its own stoppers. So we will be the one to manipulate the burettes. So hindi naman, as long as that you've reached the changing of color, meaning to say, doon mo siya is to stop. Doon mo gagamitin yung stopper ng burette. Okay? So pagdagdag ng solution, ikaw bahala sa pagdagdag as long as you can see now the changing of color. Either you can see the bad and the good endpoint. That's the time you have to use the stopper of the burette. Okay? And that's the time you've reached already the endpoint of the experimentation. I hope you've already understand what I'm saying. Okay? So the indicator is used. The use of an indicator is a key in performing a successful titration reaction. The purpose of an indicator is to show when enough standard solution has been added to fully react with the unknown concentration. Indicators must only be added to the solution of unknown concentration when no visible reaction will occur. Depending on the solution being titrated, the choice of the indicator can become key for success of the titration. Of course, indicators has a factor in identifying the success of titration. As I've said a while ago, the endpoint is basically can indicate in by using an indicator, diba? It can usually being done by using an indicator if you want to reach the endpoint. So in using indicator, this is the key on how we can eventually have the so-called success titration if we use some indicators. Okay. So there is a reagent that can use being a indicator. So what are those? Okay. Titration with an indicator. So now we can already be known what are those indicators in the experimentation titration. Okay. So let's proceed. So these are the materials for titration. I've already said this a while ago. Erlenmeyer flask or beaker, excess amount of standard solution or the titrant, a precisely measured amount of analyte. This will be used to make the solution of unknown concentration. Indicator, calibrated burette and burette stand. So here is this one is basically a description of each the importance of each laboratory apparatuses, and of course kung ano ang ilalagay nyo sa laboratory apparatuses. As I said, we have ring stand, burette, and the two solution that being mixed we have standard solution, and we have the unknown solution. Okay, I've already discussed that a while ago. So procedure. Obtain all necessary materials and clean all necessary items. That is very important in having an experimentation. Before we demo, before we start the experimentation, we have to clean, we have to sanitize all the laboratory apparatuses to avoid contamination. Okay? Measure out the precise amount of analyte and make up the solution of unknown concentration. That is actually important. Quantitatively transfer the analyte into beaker or Erlenmeyer flask. So if the laboratory has no beaker, we can use Erlenmeyer flask. Add additional distilled water until the analyte is fully dissolved. Measure and record volume of aqueous solution. And lastly, add 4 to 5 drops of appropriate color indicator into the beaker to proceed into success titration. Okay, so this is the procedure on how to start the experimentation, which is titration. Okay, so let's proceed. Swirl the beaker in order to mix the aqueous solution of the analyte and the drops of indicator. This is the continuation on the first slide. Fill the burette with an excess amount of titrant, the standard solution of known concentration, and should be in aqueous form. Clamp the burette carefully to a burette stand. The tip of the burette should not be touching any surfaces. Place the beaker containing the aqueous solution of unknown concentration under the burette. Record the initial volume of the burette. Make sure to measure at the bottom of the meniscus. So this is the procedure, as I've said a while ago, in starting the experimentation, which is called as titration. So basically, this is the explanation or description on how yung nakita nyo kanina na picture. Ganon talaga siya. Okay, so this one, mas maganda if I will be sending how to demonstrate, or I will be sending a certain link on how to perform titration for you to understand it more. Okay? Then turn on the stopcock top of the burette so that standard solution is added to beaker. This should cause a color change, so be sure to swirl the beaker until the color disappears. Continuation pa rin to sa naunang slide. Repeat the above step until the color does not disappear. This means you have reached the end point. Stop when you've reached end point, which is the unknown concentration has been completely neutralized, and measures and record your final volume of the burette. Calculate the volume of the standard solution used by subtracting the initial volume measurement from the final volume measurement of the burette. And now perform the necessary calculation in order to obtain concentration of the unknown solution. So please be informed that the steps should be in order. Okay, there is no such thing that you've already changed the first to the second step. No, it should be in order. For you to have a successful titration, you have to follow in order the steps and procedure in this experimentation. Okay, did you get the point? Okay, so now let's proceed to the types of titration. So there is a lot of types of titration. There are many types of titration with different procedure and goals. We have first acid and base titration, which is very known in the academic in the content of the analytical chemistry. Kasi this is the first one that being used in the demonstration in this topic, acid and base titration. Next is the Redox titration, gas phase titration, Complexometric titration, back titration, and the Karl Fischer titration. So here we will discuss it one by one. So now let's proceed on the acid-base titration. It is quite easy than the other titration. Why? You will identify if the unknown solution is in acid or in base. Acid-base titration depend on the neutralization between an acid and a base when mixed in solution. In addition to the sample, an appropriate indicator is added to the titration chamber, reflecting the potential hydrogen range of the equivalence point. The acid-base indicator indicates the end point of the titration by changing the color. So here in acid-base titration, it will focus on the range of the potential hydrogen. So there is a specific scale number on how can we identify the acidity and basicity of a certain substance. As we all know, the potential hydrogen level or the scale in acid-base titration is that from 0 to 14. So 7 being neutral and 1 to 6 is the acidity, and 8 to 14 is the basicity. Okay, so that is the range on how can we explain the potential hydrogen. Sorry with the word physical. The potential hydrogen scale or range in acidity and basicity of a certain substance. Okay. So let's proceed. So the final solution after titration should be neutralized and contain equal moles of hydroxide and hydrogen ions. So the moles of acid should equal the moles of base. So now here is the constant formula on how to calculate this. So we have molarity of acid, volume of acid, molarity of base, and volume of base. So molarity is equals to moles, as we all know, over liter is equals to mole per liter. So here is the formula of that experimentation. So I will not be giving you an example yet of a problem. Kasi before we will go to a problem, dapat we will perform the titration itself. Okay? So, some common indicators used in an acid-base titration. That's what I'm saying a while ago, that we will be knowing also the indicators. So, here we have in the acid-base titration, we have methyl violet, bromophenol blue, methyl orange, methyl red, litmus, bromothymol blue, phenolphthalein, alizarin yellow. Okay, so this the range, the color acidic side and the color basic side. So here, so this is the illustration. Take a look and remember this illustration, this table, because it's very important. This is one of the important topic. This is include to your exam for finals. Okay, so now let's proceed to another type of titration. We have redox titration, and it is quite different to acid-base titration. Why? Because redox titration are based on the reduction and oxidation reaction between the oxidizing agent and reducing agent. So a potentiometer or redox indicator is usually used to determine the endpoint of the titration. Some redox titration do not require an indicator due to the intense color of the constituents. For instance, in fermanganometry, a slight persisting pink color signals the endpoint of the titration because of the color of the excess oxidizing agent or potassium permanganate. So to discuss it simply, redox titration is a titration in which the analyte and the titrant react through an oxidation or reduction reaction. Okay? So that's it. That is the simply yes explanation on redox titration. Okay? And basically, if we undergo a certain type of titration like redox titration, we have to use or require a potentiometer or the redox indicator. Okay? So take note with that. So now let's proceed to the gas phase titration. So gas phase titration are titration done in the gas phase, specifically as a method for determining a reactive species by reaction with an excess of some other gas acting as the titrant. So in one common gas phase titration, gaseous ozone is titrated with nitrogen oxide according to the reaction. So that explains the component element below. Okay, so after the reaction is complete, the remaining titrant and product are quantified. So this is used to determine the amount of analyte in the original sample. So meaning to say, when we say gas phase titration, it refers generally to any titration done in the gas phase. So if there is an involvement in the gas phase, meaning to say that titration is called gas phase titration. And the element in the compound below that you are now being seen, the product and the reactant, that is a constant in the gas phase titration. Okay, so now let's proceed to the complexometric titration. Complexometric titration rely on the formation of the complex between the analyte and the titrant. In general, they require specialized indicators that form weak complexes with the analyte. Common examples are the aerochrome black tea for the titration of calcium and magnesium ions, and the chelating agent used to titrate metals ions in a solution. So meaning to say, when we say complexometric titration, it is a form of volumetric analysis in which the formation of a colored complex is used to indicate the endpoint of the titration. So there is an involvement of the volumetric analysis. If the volumetric analysis is being formed and being produced a colored complex, so that is being used in indicating the endpoint of the titration. Okay, so I hope you get the point on the differences between each type of titration. Let's proceed to the another type of titration, back titration. Back titration is very simple because it is the reverse process. You have to go back to the beginning of the process if you did not done successfully your titration. So back titration is titration done in reverse instead of titrating the sample. A known excess of standard reagent is added to the solution and the excess is titrated. A back titration is useful if the endpoint of the reverse titration is easier to identify the endpoint of the normal titration. As with precipitation reaction, back titration are also useful if the reaction between the analyte and the titrate is very slow, or when the analyte is non-soluble solid. So that's what I'm saying a while ago, that back titration is a titration in which we have to go back to the beginning of the step and perform it in orderly. Okay, if you did not done the titration process successfully, you can go back, and that kind of titration is called back titration. And you have to follow also the step in order. Okay, babalik ka lang, back titration. If your titration is in not resulted in a successful way. Okay, so that is back titration. Next is the Karl Fischer titration. It is a potentiometric method to analyze trace amount of water in a substance. A sample is dissolved in a methanol and titrated with Karl Fischer reagent. So the reagent contains iodine, which reacts proportionally with water. Thus, the water content can be determined by monitoring the potential of excess iodine. So, meaning to say, or basically, Karl Fischer titration is a classic titration method in chemical analysis that uses colorimetric or volumetric titration to determine the trace amount of water. What is basically the principle of a Karl Fischer titration? The principle is based on the oxidation reaction between iodine and the sulfur dioxide. If the water reacts with the iodine and sulfur dioxide to form sulfur trioxide and hydrogen iodide, and that result with the endpoint is reached when all the water is being consumed. So that is Karl Fischer titration. And now let's proceed to another slide. For the end of this topic, we have titration curves. So the graphs of titration curves effectively shows the relationship between the potential hydrogen of the solution of unknown concentration as the standard solution is added to it in order to reach neutralization. So here it is basically being done if we already done in the experimentation process, in the calculation process, then if the result is successful, is the result as successful, now you have to to plot it in a curve. So here, because as I've said a while ago, that the scale or the range of it is 0 to 14, because the potential hydrogen or the scale range of the substance is from 0 to 14. So here, so this is the range in which the indicator that being used is metal orange, and the indicator that being used is phenolphthalein. Okay, so that's it. That is the end. We've already reached our end for analytical chemistry. So I hope you've already understand the topics here. And if you have some confusion, if you have some question, you can raise it in the group chat or either direct message me. Thank you very much, BSMT1A. I hope you've enjoyed already listening to and understanding also to the lesson that I've been discussed in analytical chemistry. Let's see each other soon for the face-to-face class. I hope this coming second semester we can have a face-to-face class. So thank you so much and have a great day.